Welcome you all. So in this session, we are going to see about the invariant reactions, the various invariant reactions. Okay, so invariant reactions are nothing but the reaction that takes place at constant temperature. Okay, that is invariant reaction. So there are four types of invariant reaction that takes place in the phase diagrams. You can find these invariant reactions in the phase diagrams. Okay, if you take the iron carbide equilibrium diagram, you can find three types of the phase reactions. Okay, so one is the Eutectoid phase reaction, Eutectoid reaction, then Eutectic reaction, and Peritectic reaction. Okay, so in this session, we are going to discuss each reaction in detail. Okay, come, let's go to the session. So the first reaction is eutectic reaction. Okay, so what is eutectic reaction? So from here, you can see that this eutectic reaction, it may happen in two ways. Okay, so if you heat the material, okay, if you heat the material, then it will happen like the two solids will combine and it will give you a liquid. Okay, while heating. For example, if you are cooling from the liquid phase, then it will give you two solids. Okay, that is eutectic reaction. A eutectic reaction is a special type of phase reaction, a three-phase reaction. So it is actually a three-phase reaction. And here we have one liquid phase and two solid phase. Okay, so the two solid phases are alpha and beta. Okay, let's say alpha and beta are the two solid phases. Okay, so it is defined as upon cooling, a liquid is transformed into two solids. Okay, that is eutectic reaction. Okay, so this is an example for eutectic reaction in a phase diagram. Okay, so in this phase diagram, you can find it is a binary phase diagram. Okay, where we have two types of material. Okay, on the left hand side we have 100% A. Okay, so let's say A and B are the two materials. Okay, or two metals. Okay, and B is the another metal. Okay, in the extreme right side we have 100% B. At a particular composition, we have we can see a eutectic point. Okay, so in this phase diagram, you can see how to interpret the phase diagram. Okay, that is a very important question here. Okay, so how to interpret the phase diagram. So here we have 100% A metal. Okay, and here we have 100% B metal. Okay, so if here we have 100% A means then at this point we have 0% B. Okay, and similarly, the opposite side, if it is 100% B means then here we have 0% A. Okay, which means at the extreme two sides we have a purest form of metals. Okay, so the metal A has a particular melting point. Okay, in the x-axis we have a composition and in y-axis we have a temperature. Okay, so here this is the melting point of metal A and in the opposite side this is the melting point of metal B. Okay, at a particular composition, this A and B, particular composition, these two material are mixes and it will be having a minimum melting temperature. Okay, so this is the invariant line. Okay, and these are these two lines are intersects here, and this portion is called liquid plus alpha, and this portion is called liquid plus beta, and this is a beta, and this is alpha, and this within this region we have alpha plus beta. So here alpha, beta, liquid are the different phases. Okay, so this is the point where the melting point is very low. Okay, this point is called eutectic point. Okay, for example, if you consider, so I'm taking this particular composition. Okay, say let's say 90% A and 10% B, metal B. So if you take this particular percentage, and here we have the upon cooling. So this is the line which separates the liquid and liquid plus alpha. Okay, and this particular region, the material is in the form of liquid plus solid. Okay, when when the temperature reaches here, then only the material will get a solid form, that is alpha. Okay, then again if the temperature temperature get reduced, okay, it will come to alpha plus beta. So this particular temperature range, the material will be in the liquid plus solid phase. Okay, whereas at eutectic point, there is no liquid plus solid phase. Okay, actually, the liquid is directly converted into solid. Okay, but the solid what we have is the two phases. Okay, alpha plus beta. So this is the eutectic reaction. And the next reaction is eutectoid reaction. Okay, this is also an invariant reaction. So this particular reaction is also takes place at the constant temperature. Okay. Like the previous eutectic reaction, this eutectoid reaction is also takes place at constant temperature. Okay, so you can find this eutectoid reaction in iron carbide equilibrium diagram. Okay, so this Eutectoid reaction is a three-phase reaction by which on cooling, a solid transforms into two other solid phases at the same time. Okay, so in the previous reaction, upon cooling, a liquid transforms into two solid phases. Okay, let's say alpha and beta. Okay, here in Eutectoid reaction, this is also a three-phase reaction in which upon cooling, a solid transforms into two other solid phases. Okay, that is eutectoid reaction. So here you can see here. So this is the reaction that takes place in the iron carbide equilibrium diagram. Okay, so this is the general eutectoid reaction. So solid gamma, okay, upon cooling, the solid gamma, that is the first phase, solid gamma transforms into two solid phases, that is solid alpha and solid beta. Okay, so this reaction takes place in iron carbide equilibrium diagram. So in that, the solid gamma is nothing but the austenite. Okay, upon cooling, the austenite phase is transformed into two solid phases. Okay, one is a ferrite phase and the another solid phase is the cementite phase. Okay, so this is the eutectoid reaction. So here you can see, so this is the eutectoid reaction. So this is the actual phase diagram that is taken from iron carbide equilibrium diagram. Here you can see a particular portion. This is not a complete iron carbide equilibrium diagram. Particular portion is given here. Okay. So at the left hand side we have 100% iron, which means it is a purest form of iron, and here we have a 0% carbon. Okay, so this is the carbon weight percentage is increases in this way. Okay, so here we have a 0.5% weight percentage carbon, and here this is 1 weight percentage carbon, 1.5 weight percentage carbon. So like that it progresses. Okay, and in y-axis we have a temperature in degrees Celsius. So here, so this is the point where the eutectoid reaction takes place. Okay, so what is the definition of eutectoid reaction? So eutectoid reaction is a three-phase reaction by which upon cooling, one solid phase is transforms into two solid phases. Okay, so this is this one solid phase, that is gamma austenite. So upon cooling, it transforms into two solid phases, alpha plus Fe3C. So this is the eutectoid reaction. So this eutectoid reaction happens at 723 degrees Celsius. So this is the invariant line. Okay. And this is also another invariant line. This line, this is 1130 degree Celsius. Okay. At this temperature, the eutectic reaction took place. Okay. Eutectic reaction takes place in iron carbide equilibrium diagram. And now let us see the differences between eutectic and eutectoid reaction. Okay. So in both eutectic and eutectoid reaction, both are involving three phases. Okay. So first, let us see the definition of eutectic reaction. So eutectic reactions are chemical reactions in which a liquid transforms into two solid phases at the same time upon cooling. Okay. Whereas in eutectoid reaction, This is also a chemical reaction in which a solid transforms into two other solid phases. Okay, in eutectic reaction, liquid transforms into two solid phases. Whereas in eutectoid reaction, a solid, okay, one solid phase transformed into two another solid phases. Okay, this is eutectoid reaction. Next, phase transformation. Okay, based on phase transformation in eutectic reaction, liquid converts into two solids. Okay, whereas in eutectoid reaction, solid converts into two liquids. Okay, that is gamma arsenide is transformed into alpha plus Fe3C. Okay, so this is the eutectoid reaction. Then example. Okay, so here for eutectic reaction, it is a crystallization of solids from a solution. Okay, which means a liquid upon cooling, liquid transforms into two solid phases, that is alpha plus beta. Or in with respect to the ion carbide equilibrium diagram, the liquid transforms into gamma plus Fe3C. Okay, gamma is the one phase and Fe3 is the another phase. Okay, and eutectoid reaction example is steel production in perlite structure. So perlite is nothing but the alternate layers of alpha and Fe3C. Okay, that is the perlite structure. And temperature. So with respect to temperature, the eutectic reaction occurs at the eutectic temperature of the components. Okay, for the eutectic temperature in ion carbide equilibrium diagram is 1130 degree Celsius. And for eutectoid reaction, it is 723 degrees Celsius. It is the recrystallization temperature. Okay, so this is all about the differences between eutectic and eutectoid reaction. Okay. Now let's go to the next slide. That is peritectic reaction. So this peritectic reaction is also takes place in ion carbide equilibrium diagram. So this peritectic reaction is also a three-phase reaction. Okay, in which upon cooling, a liquid and solid phase will together form a second solid phase. Okay, this is the peritectic reaction. So you can find the peritectic reaction here. Okay, so this is the point where peritectic reaction takes place. Okay, and this is the invariant line. Okay, this peritectic reaction takes place at this temperature. So here you can see liquid plus solid. Okay, so upon cooling, this liquid plus solid will together form a second solid phase, that is austenite. Okay, this is peritectic reaction. And these reactions are rather sluggish as the product phase will form in at the boundary between the two reaction phases, thus separating them and slowing down any further reaction. Okay, so okay, so this is what this is the peritectic. This is about the peritectic reactions. So next one is the peritectoid reaction. So in this peritectoid reaction also three-phase invariant reactions where the two solids are combined together to form a third solid phase. Okay, in eutectic reaction, upon cooling, liquid phase is transformed into two solid phases. Okay. In eutectoid reaction, upon cooling, one solid phase is transformed into two solid phases. Peritectic reaction, one a liquid and solid phase will together forms a second solid phase. Whereas in peritectoid reaction, two solid phases will together forms a third solid phase. Okay, this is peritectoid reaction. So these four reactions are very important, and you can find any one of these or two or three of these, okay, phase reactions in the in the phase diagrams. So Here we can see all the phase diagrams are given in a single slide. Okay, in eutectic reaction. So upon cooling, so all these are under cooling condition. Okay, when you are cooling, you will get these things. Okay, under cooling, upon cooling, liquid will give you two solid phases. That is eutectic. Then peritectic means one liquid and solid phase will give you the second solid phase. That is peritectic reaction. And Eutectic eutectoid reaction where one solid phase will, upon cooling, one solid phase will give two solid phases. That is eutectoid reaction and peritectoid reaction. The two solid phases will combine together and it will produce a third solid phase. That is peritectoid reaction. And another one is monotechnic reaction. Here, one liquid phase will give you liquid and solid phase. Okay, this is monotectic reaction. So with this, I wind up this session. Okay, we will see the iron carbide phase diagram in the next session. Okay, thank you.